We defined momentum yesterday in two different ways. One was kind of our everyday understanding of momentum, and the other was our technical, our real scientific definition of momentum, the definition that you'd need to put down if you ever had a question on a quiz or a test. Give me one of them. I don't care which one you give me, the real one or the everyday understanding of momentum, Matt? Yeah, that's not the technical definition, but it's the one that honestly that I like better because I think it helps us to understand it more. It's how difficult it is to stop something. The more difficult it is to stop something, the more momentum it has. What are the two factors? What are the two factors that influence how difficult it is to stop something? Say it. Mass and velocity. Therefore, the real definition of momentum is going to be the product of mass and velocity. Mass and velocity both make things difficult to stop. Mass and velocity both give something momentum. So the product of mass and velocity is the momentum. I showed you two pictures yesterday. And we related these two pictures to momentum, but also to another term called inertia. Do you guys remember what the difference is between inertia and momentum? Yeah, just. Yeah, inertia is about changing the motion, but isn't momentum as well? Like how hard is it to stop something? That's changing the motion of something, right? It's almost like momentum is kind of like we don't think of it as a specific kind of inertia, but it's almost like that, right? Momentum is how difficult it is to stop something. Well, the more inertia something has, the more difficult it is to stop something too, right? If it's moving. But if it's at rest, the more difficult it is to start something. Inertia is a more general term. It's how difficult it is to change the motion of an object, how difficult it is to make something speed up or slow down or start something or stop something. So inertia is going to be dependent upon what? If momentum is mass and velocity, inertia depends upon just mass. Thanks. Momentum is a vector, of course, and the equation that describes momentum, of course, is P is equal to m times v. It comes right back to the definition. Mass, the product of mass and velocity. What were the units that we used for momentum? You can get it from this, right? Yeah, what is it? Yeah, kilograms, meters per second. So, of course, that depends upon us using kilograms for mass and meters per second for velocity. What if we got a mass in grams? What if we said, I don't know, 236 grams? We want to convert that to kilograms. Anybody know what it would be? Yep, right? Yeah, it's 0.236 kilograms, right? We're going to divide by 1,000. How many people think sometimes that they might forget the conversion factor? 1,000, is it 100? Yeah, it's easy to do, isn't it? Easy to forget that. Okay, there's so many conversion factors. I want you to check your data sheet for a second. Everybody open up the data sheet booklet that I gave you yesterday. Open up to the second page, in the middle of the second page. Go all the way down to where it says kilo, K, just 10 to the 3. What does it tell you? The conversion factor is not 100. The conversion factor is 1,000. If you think you might have any chance of mixing up kilo with centa or milla or anything like that, then just double check it on your data sheet. It's there for you. So we would, in fact, divide this by 1,000, right? 0.236 kilograms. How about this one? 24 grams to kilograms. What's that one going to be? Yep. Yeah, it's 0.024 kilograms. Now, if you're anything like me, I don't know why I have this problem. I don't know why still. But I do sometimes, not often, but occasionally I have this problem where if I'm converting by moving decimal places, I seem to make a mistake moving the decimal places. Not so much with the first one. I don't really have a problem with those ones. But when I'm moving it over and there's going to be a 0 in there or 2 zeros or 3 zeros, I sometimes get mixed up as to where I'm counting. Maybe you don't. If you don't, that's great. If you do, then I'm going to suggest you do what I do to avoid making that mistake of moving the decimal place over the wrong number of places. Okay. For this one, I just move it over to here, and I get it every time. But for this one, sometimes I mess up. All I do for this one is look at my data sheet and say, oh, it's a conversion factor of 10 to the 3. So I'm going to say 24. I'm not going to move the decimal place over. I'm just going to say 24 times 10 to the minus 3 kilograms. Then I don't have to worry about moving the decimal place over, right? Is that scientific notation? No. 2.4 times 10 to the negative 2 would be scientific notation. That's not scientific notation. Who cares? It's right. And I didn't have to worry about moving the decimal place over. Listen, if you're good at moving the decimal place over, don't worry about this. But if you have trouble with it, that's the way that I get around making a mistake moving the decimal place over. Okay? How about this whole meters per second thing? One of the common conversions is going to be kilometers per hour to meters per second. Let's go with 72 kilometers per hour. I want to convert that to meters per second. You guys remember how to do that? You guys remember what the conversion factor is? There is a shortcut, and there's a that allows us to use a conversion factor to find it right away. Yeah?
Well, I don't know, maybe the right away one, but what you can do is you can multiply 72 by 1,000.
Yeah, absolutely. 72 times 1,000 gives you meters, and then divide it by 3,600 gives you seconds. So that gives us meters per second. Good, absolutely. Remember the shortcut? If you divide by 3.6, it gives you the exact same thing. So that ends up giving you 20 meters per second. Now, I always remember that it's divided by 3.6, but when I was in grade 11 and grade 12, I didn't always remember that. Sometimes I'd mess up. So what would I do? Sometimes I just guess. That's okay. Guessing's okay, as long as you check your guess. Let's see, I got 72 kilometers per hour, and I'm like, I don't remember. Is it multiply or divide? I'm going to guess it's multiply. When I multiply 72 times 3.6, I end up getting 259 meters per second. Is that reasonable? Like, stop and think about it for a second. Is 259 meters in 1 second reasonable? No, that's almost 3 football fields in 1 second. It's not reasonable. Okay? It is, yeah, it's reasonable for a jet, but not for something going 72 kilometers per hour. So if you guess wrong because you see that it's not reasonable, that's okay. Just guess again. If I multiply by 3.6, doesn't work out, well then divide by 3.6 and we get 20, and that's a lot more reasonable. Try this one. We've got some kind of comet or some kind of thing out in space going at 2.5 kilometers per second. That's fast. Okay, for a car or a person, that's not reasonable. But for something in space, maybe it is. I want to convert that to meters per second. How would I do that? Yeah? Yeah, that's all I got to do is multiply it by 1,000. I've already got seconds on the bottom. The only conversion to do here is kilometers to meters. 2.5 times 1,000. We could say 2,500. Or we could just say 2.5 times 10 to the 3 meters over seconds, because seconds is already there. 2,500 meters per second. Make sense? We're not going to see something like that very often, if at all, to be honest. We want to be ready for it, though, just in case. I'll tell you what, if you see this on a test and it's multiple choice, I guarantee you one of the 4 options depends upon you dividing that by 3.6. That's wrong, but you can imagine how easy it would be. Let's say you're writing your diploma exam in in January. And you've been writing for 2 hours and 40 minutes. Your mind is shot, it's gone. And then you see a question that says 2.5 kilometers per second. How easy would it be to just divide that by 3.6? And that will be there. That will be there as an option. Just be aware. Hey, be alert, be aware, and remember that you don't have to do that. Just multiply it by 1,000. Okay? All right. We did 2 questions yesterday, page 451. Those are both okay? Yeah? We also did one more example, which I won't go through right now because we'll do a couple more practice questions of that in just a second here. That was good too, though? All right. Let's take a look at a multiple choice question that appears on the board right now, but also appears in your worksheet booklet that I gave to you yesterday on page 11. So if you want to look at it on the board, that's great. If you want to have a closer look on page 11 of your worksheet booklet, that's great too. Give you about 2 minutes, see what you can do with that, and then we'll take a look at it as a group. Here's our question. So the batter hits a fly ball. The 0.13 kilogram baseball moves at a rate of 20 meters per second at a point where it's 5 meters above the ground. Right? Picture it. Like literally, picture it, visualize it. Do you see the baseball? Do you see the baseball 5 meters above the ground? Ethan, what does it say on the baseball? There's a word on the baseball. What does it say? Exactly. There you go. He sees the baseball. Okay, picture the baseball. Is there marks on it from bats? Like no paint on it from bats? Dirt? Is it kind of scuffed up? No, it's like a brand new baseball. All right, there you go. Good. You got a baseball that's unscuffed, unpainted, good shape, says Spalding on the side of it, and it's moving at 20 meters per second, 5 meters above the ground. We want to know what its momentum is where? When it hits the ground. So we're given a velocity of 20 meters per second up here, but that's not the velocity we want. If we want to find the momentum down here, then we need to use the velocity down here. So we got to find that. And that's an easy mistake to make. Right? You look at this and say, oh, I got a mass, I got a velocity, m times v is 2.6. It's wrong because it's the wrong velocity. Don't make that mistake. Don't be careless. Don't just blindly look at givens and say, I got it. Think about what's going on. Picture it. Okay, givens are important, but just as important, probably more important, is thinking about the question. Seeing what's going on, picturing the question. All right, so we want to find the speed or the velocity as it hits the ground. How are we going to do that? This is real similar to something we did yesterday, right? Last example we did, in fact. Probably VF squared. Yeah, let me move it over here. Let's rearrange that. VF is equal to the square root of VI would be 20. A would be negative 9.1. D would be negative 5. Who does that? What does that work out to be? 20 something, I think. Wasn't it 26? 22? 22.31? And then we're going to say P is equal to M times V. Now, technically, when we do that, the velocity is negative, but since we're only looking for the magnitude of the momentum, it doesn't really matter if we plug that negative in or not. What do we got? 1.130 times 22.31 gives me 2.90. Is that good? Anybody do this to find VF? Anybody say EI equals EF? Anybody do that? MGH is equal to 1 half mv squared. Actually, it's not MGH equals 1 half mv squared. It's 1 half mv squared plus MGH, because there's kinetic and potential to start off, equals 1 half mv squared. Yeah? That makes sense? That would get us VF as well. Let me show you something, though. Let me rearrange this. Let me take this over to the left side, take this stuff over to the right side. I got 1 half mvf squared equals 1 half mvi squared plus mgh. With me so far? Is that legitimate? Is that okay to do mathematically? Sure. I can do whatever I want now to a term as long as I do it to every term. Let's divide by m. M's cancel. Let's multiply by 2. 2 times a half is 1. I get VF squared. 2 times a half is 1. I get VI squared. Plus 2 times GH is 2GH. What does that look like? It looks like this, right? VF squared is equal to VI squared plus 2 times, what's G? Acceleration. What's H? The displacement, yeah. Make sense? Either way is going to get you the same answer because it's really the same thing. Let's try another one. Question number 2, also appearing on page 11 of your worksheet booklet. All right, let's have a look here now. Tell you what, this is a good question It's a good question because it relates to momentum and P equals M times V, but it's also a good question because it illustrates something that causes a lot of us to make mistakes, especially at that 2.5 hour period of your exam when your mind is kind of gone now. We read through this question. I want you to stop me when I reach something that you think might lead to a silly mistake, especially if you're not thinking clearly because you've been writing an exam for 2.5 hours. A particular supertanker is fully loaded with oil and has a mass of 1.0 times 10 to the 9 kilograms. The supertanker has a cruising speed of 20 kilometers per hour. Let's circle that in red. When we see something like that, let's circle it in red. It doesn't mean we're not going to make the mistake of forgetting to convert it, but it reduces the chance. If we draw attention to it, it reduces our chances of messing up on that. We still might, but we're less likely to. One way to stop the ship is to reverse its engines. At maximum reverse thrust, the ship takes 32 minutes to stop. If this ship takes 32 minutes to stop, what do we know about this ship? It's hard to stop, and it's hard to stop because it has a lot of momentum. And it has a lot of momentum because it's heavy. It's not moving all that fast, right? What's the momentum of this supertanker? Well, to find the momentum, all we're going to do is say m times v, but we need to know what v is in meters per second. I think that works out to be 5.55, isn't it? Don't forget to do that conversion. Now, how would you express this? For a lot of you, this is the first time you've done a numeric response question. You will see on your unit tests and on your diploma exam, for each numeric response question, a set of boxes that looks like this, 4 of them. They're looking for the value of B. B is the base here. B times 10 to the W. B times 10 to the W. We want B. So the answer is 5.56. Good? The crappy thing about this is you express that wrong. You put 556 or some other thing. You know what you're doing. You get it wrong. You lose 2% on your exam because you expressed it wrong. So if in doubt, especially on unit tests, if in doubt, ask me, and I can help you out with that, okay? All right, we got another example here. This is a bit of a new one. Take a read through it. Okay, you've read through it now. Where do you go with this? You want to find a momentum, but I don't know what M is. I don't know what V is. How do you find P when you don't know what M is and you don't know what V is? We're going to use a strategy that I call variable value changing. Variable value changing. We're changing the value of variables without knowing what they were to begin with. Look at what I'm doing. Okay, the mass is decreased to 1/3 of what it was. What was it? I don't know. But now it's 1/3 of, I don't know. The mass is, the speed increases to 4 times what it was. What was the speed? I don't know. But now it's 4 times, I don't know. 4 times what it was. It doesn't seem like I have enough information to solve for momentum when I don't know what M was or what V was. So here's what I want to do. I want to write down an equation, a relevant equation. And I've done that. The relevant equation here is momentum. P is equal to M times V. I'm going to put a little subscript in there. It's an O. It stands for original, the original momentum. Before I make any changes, before I decrease the mass or increase the velocity, momentum is M times V. And it's also 2.45 times 10 to the 2. This isn't rocket science so far. All I've written down is an equation for my data sheet and a number that they gave me in the question. I've basically written down givens, right? I haven't had to do anything yet. This is what my momentum was. But that's not what I want. I want what my if I could say it, what my momentum becomes. So here's what I'm going to do now. If my original momentum was m times v, or 2.45, then my new momentum is what? Well, let me let you know a little secret. Yesterday when I told you momentum is given by the equation m times v, I lied. Momentum is not given by the equation m times v. Momentum is found by the equation mass times velocity. We almost always represent mass by m and velocity by v. But we could represent mass by whatever we wanted. We could call it q if we wanted. As long as you, and everybody else understood that mass was given by the symbol q, then q times v would work fine for momentum, right? We can call it whatever symbol we want. We just usually call it by the symbol m. We're going to change that here. It's still mass times velocity, but the mass is no longer going to be given by the symbol m. The mass is going to be given by the symbol 1/3 m. That's my new mass. If my mass was m, my mass is now 1/3 m. My velocity was given by the symbol v. Now my velocity is given by the symbol 4v. Make sense? My old momentum was m mass times velocity. My new momentum is mass times velocity. I'm just using different symbols to represent mass and velocity. That's all. Now I want to simplify this by pulling these numbers out front. 1/3 times 4 is 4/3. Right? Just if I was multiplying it by 4 halves, it would be 1 times 4 is 4. 3 times 2 is 6. We just multiply the top numbers, multiply the bottom numbers. 1/3 times 4 is 4/3. M times V. But look what I've got here. The very first thing I did was say that M times V is 2.45. My new momentum is 4/3 times M times V. In other words, my new momentum is 4/3 times 2.45 times 10 to the 2. How did I know to sub that in? Look, it's the very first thing I wrote down. M times V is 2.45, so why wouldn't you sub that in? So we're going to calculate that now. Do the math there, we get 327. See what I've just done there? I found out what the new momentum is just by changing the values of variables without even knowing what the values were to begin with. It's okay, because I have a tool called variable value changing. What do you got to do with that tool? Get an equation, get a relevant equation. Set that equation equal to the original amount. Instead of value equal to that if you have it. And then write down your new equation with your new symbols. 1/3 M, 4V. And pull those numbers out in front to make it look as much as possible like this. And then sub in a value, and you're done. Is that okay? Listen, if I had to make a guess, if I had to put money on it, I would guess, and I would put money on this, that you will get a question on your diploma exam involving variable value changing. I don't know if it'll involve momentum or some other topic that we do this year, but the way that we do it ends up being the same. Just the equation might be different, that's all. I would put money on the fact that you'll see one of those on your diploma exam. I don't need to put money on the fact that you'll see one of those on unit tests. I can tell you right now, you will see at least a couple of those this year on unit tests. Okay, be ready. We know we're going to see it. Be ready. A couple questions that appear on page 452 that I'd like you to take a look at. But before I set you free to do them, I want to point out a mistake they made, not so much in the question, but rather in the answers. It's not 9.28. It works out to be 3.09. Take a read at the first question. Take a read through the first question and see if you can figure out what mistake they made. Don't calculate anything. Just look at what might lead to a mistake there. If you find it, it's the mistake that they made. All right, let's have a look. Many modern rifles use bullets that have less mass and reach higher speeds than bullets for older rifles, resulting in increased accuracy over long distances. The momentum of a bullet is initially 8.25, all right? What's the momentum if the speed increases by 3 over 2 and the mass decreases by 3 over 4? What's the difference between the mass and the velocity here? What's happening to the mass? What's happening to the mass? Mass is decreasing, right? I don't care how much it decreases by, I care what it becomes. So here's the deal. If the velocity was v, now the velocity is going to be 3 over 2v. Agree? If the mass was m, now the mass is going to become not 3/4 m, 1/4 m. What do you think they used? 3/4 m. Okay? Because it decreased by 3/4, it becomes 1/4, and that's what I care about, what it becomes. All right? Let's get to work on those questions now. Time to have a look at question number 2 here, everyone. Number 2 says, during one part of the liftoff of a model rocket, its momentum increases by a factor of 4 while its mass is halved. Does that make sense? You picture this rocket taking off, right? Its momentum goes up dramatically, okay, as this rocket starts going faster and faster through the air, but its mass decreases dramatically. It doesn't take very long for the mass of the rocket to decrease by a huge amount because it's burning so much fuel as it goes up into the air, right? The velocity of the rocket is initially 8.5 meters per second upwards. What's the final velocity during that time of travel, or during that time interval? In both classes, with you guys and the other class, people are looking for some other equation for speed. Like, oh, VF squared is equal to VI squared. Listen, you want to find a relevant equation. What's the concept that applies here? Like, what's going on? This is momentum, right? We have a momentum and a mass, or at least it talks about momentum and velocity and mass. Use the momentum equation. Just rearrange it. There's my equation for velocity. There's my original velocity, which is 8.5. My new velocity is what? Well, it says the momentum increases by a factor of 4, and the mass decreases by a factor of a half. That's 4 divided by half. 8. Don't make it 2, right? 4 divided by half is 8. Do it on a calculator if you have trouble with that. What's P over M? Look, 8.5. 8 times 8.5 is 68. Good? The answer to the first one is 3.09. Good? All right. I'm going to give you a stack of questions now that you're going to work on in class here. Starting on page 453, number 1, 2, 5 to 9, 11, and 13 to 16. We can scroll, you can get up and scroll around here, or I can scroll around here if you wish, in order to get to the questions you need. Unfortunately, we don't have the login figured out for our textbook yet. It's still not working right. So you're going to have to look off of here or snap a photo of Ethan's book or something like that. All right, let's get to work.